So these are the second half of the chapter 8 notes, and we want to continue talking about kind of circular motion, and then we're going to also introduce banking when we essentially throw the circular motion on a curve. So what is the maximum speed of a 1500 kilogram car can make without sliding around an unbanked curve of radius 50 meters if the coefficient of friction is 1.0? All right, so here, remember that the centripetal force, Fc, equals some other force. In this case, it's going to be friction that keeps the car on the road. So if we substitute, if I've got mv squared over r equals mu mg, the mass cancels out, and so I can rearrange this for v is going to be the square root of mu r g. And so if I plug the numbers in, I've got 1, I've got 50, and then I have 10. So essentially the square root of 500 gives me 22.4 meters per second. And okay. So here's another example. A car with a mass of 1350 kilograms traveling at 55 kilometers per hour when it encounters a curve with a radius of 40 meters. What's the minimum coefficient of friction needed to keep the car on the road? So first thing we need to do is change this to meters per second. I won't go through the whole process. It comes out, it's 15.3 meters per second. So it's the same situation we had in the last example. We've got mv squared over r equals mu mg. Again, it's friction that's keeping the car moving in a circle. Masses cancel out, and so for this one, it wants to know what mu is. So mu is going to be equal to v squared over rg. So if I've got 15.3 squared divided by 40 times 10 gives me a coefficient of 0.58. And again, there are no units on the coefficient of friction. And then for the second part, if the pavement is wet and oily and we're reducing the coefficient of friction to 0.3, what's the maximum speed it can have? So we're going to use the same equation. It's just now we're going to solve for that velocity again, just like we did in the last problem. And it's the square root of mu rg. And so I'm going to have 0.3 times 40 times 10. And this is going to equal 11 meters per second. So we have to slow it way down if we're going to reduce the friction. Okay, so now what do you do if you don't want to rely on friction? Well, you have to bank the road. And so this is not the money kind of banking, but when a car runs a flat curve, it relies basically on friction alone to keep it on the road. And so the radius has to be fairly large to allow higher speeds without sliding. If I want the radius to be smaller and still allow the high speeds, like on an interstate or a racetrack, the solution is to bank the road at an angle. And what that does is that a component of the normal force helps keep the car on the road. So here's an example. I've got a banked road free body diagram. So here's my car on the incline. I'm looking at essentially at the back end of the car, so it's moving into the slide. And as it goes around this circular track. So I have the weight pulling straight down, I have the normal force perpendicular to the surface. And what I'm interested in is what is the force that's pointing to the center of the circle, because that will be my centripetal force. And so for here, I need to line up things that are just perfectly vertical and horizontal, which means it's the normal force that needs to be split into components. And so if I split the normal force into components, this is the angle of the incline. And so this is the side that is adjacent, and that's why that's n cosine. And then we have an n sine component. And so here, if the centripetal force is equal to this, then the car will stay put. It won't start sliding up the incline and going straight. So notice that you've got n sine of the angle is going to equal this centripetal force, and you've got n cosine equal to the weight, or mg. So for this particular type of problem, we're going to set those two equations equal. So let's just go with green. So I've got mv squared over r, the centripetal force, equal to n sine of the angle. And I've got n cosine equal to mg. So I'm going to use this equation and solve it for n. So that's going to be mg divided by the cosine of the angle. So what I'm going to do is I'm going to take this and I'm going to put it in up here. So when I do that, I end up with mv squared over r equals, and then I'm going to have mg sine divided by cosine. And a couple cool things happen here. The masses cancel, so the mass doesn't matter again. And then this is equal to the tangent of the angle. So now if I'm rearranging for the velocity, it's going to be the square root of rg times the tangent of the angle. And so now if I plug numbers in here, I've got 50 times 10 times the tangent of 15. And this is going to give me 11.6 meters per second. Okay, so the big thing again is just looking at setting these two equations. These are the two equations from the free body diagram, and we just solve one for the normal force and plug it in. And we end up with sine over cosine, which is equal to the tangent. So the other thing is, if I have objects that are moving around a planet, for example, in a circular orbit, what keeps it in the circular orbit is gravity. Or gravity is the acceleration that keeps it in that circular orbit. So we have v squared over r. And so if we want to find then the velocity of how it's orbiting, it's the square root of rg. The other thing is, if we're moving objects in a vertical circle, like if we're swinging a bucket of water, there'll be some velocity. So here would be a normal situation where you have a normal force because this object is pushing against the curve. And so there is a net force here. This would be a slightly different example. So now this is like the top of a loop-de-loop. So you're going upside down. Weight's pulling you down, but essentially at a magical spot, there is no normal force here because we are just not touching whatever it is we were touching before. So here's an example where if gravity is too big, then the water will fall out of the bucket. But here's the situation I was talking about. At that very top, if we've hit that critical speed, the normal force here will actually be 0. And so the only force that's pointing to the center and keeping this thing moving in a circle is the force of gravity. So that would apply to this example here. If a car drives over the top of a hill that has a radius of 50 meters, what maximum speed can the car have without flying off the road at the top of the hill? Well, if just before it flies off, or just as it flies off, there is no normal force. So the only forces that you have going on are, you have mv squared over r equals mg. masses cancel, so if I want to find v, it's the square root of rg. And so if I plug the numbers in, I have 50 for r, I have 10 for gravity. Square root of 500 is 22.4 meters per second. And so that is the end of the chapter 8 notes.